Class, we are now on section 3.2 of the periodic table. We are going to start with Dmitry Mendeleev. He is a Russian chemistry professor who put together the elements arranged in a certain way. So by 1860, 60 elements were known, and Russian scientist Mendeleev categorized these elements into a table based on their atomic masses, in increasing atomic mass. He also grouped elements that had similar properties, such as ones listed, which I haven't listed here, I think. Yeah, I'm going to show you. I'm going to go through this. So you will start looking at the periodic table different, as not something as foreign, and you will understand how and why this is grouped the way it is. So Mendeleev's table was basis for the periodic table we use today, which is organized by mass and properties. There was other people that organized the periodic table in different ways, but his was the one that was the foundation, and then we built upon it to what we now have. Okay, so here's the periodic table. It's set up with the elements. So these letters represent each a different element, and it's usually one or two letters. And the thing is that if it's two letters, the first letter is capitalized, the second letter is not. If you capitalize both, it's wrong. It's telling me, for instance, that you are, what are the reasons? We'll show you. If you have carbon here, and you have oxygen. Both are capitalized. So you write CO, that tells me you have carbon and you have oxygen. If you write cobalt, you write with a small o. Cobalt is not equal to carbon and oxygen. So how you write things in chemistry, you may think they are minor. They are not. They represent something entirely different. So you need to pay attention to how you write stuff. This going across is a row. We call these rows. We have 7 rows. So the first row is hydrogen and helium. The second row, it starts with lithium and ends in neon. Third row is sodium and ends in argon. This is potassium and ends in krypton, and so forth. There are 7 rows. Where does these rows fit in? Well, what you don't see, and you can Google and you can see what the periodic table is. These here, if you see, this is 57, this is 58. These actually stretch these bottom 2 rows out, where this would go out this way and this would go out this way. So this actually fits right here into this section, but this is how we normally look at it, because I'm just going to leave it at that. Right now we're going to focus on just this top part. So let me go through. So periods, anything across. This is period 1, period 2, period 3, period 4, period 5. We now also have groups. Those are the columns. They go downward. Column 1, column 2. Now I want to focus on something. If you look at old periodic tables, they will have Roman numerals at the top. They will have it, see, some of them start with 1 and 2 and then go to 13, 14, 15. The other ones start with 3A and go to 8A. You'll see this is 3B to 12B. There are differences. Your book is focusing it as the bold, 1A, 2A, 3A, and so forth, 8A. These are just numbers without letters, 3 to 12. And this is, so 1A, 2A, these go together. So these 2 columns, and then over here. This is separate. We will cover that in a while. But the periods are rows going across. So this would be, if I'm right, horizontal lines across. Vertical is the groups. We call these families. Why do we call them families? Because, as I said earlier, he grouped elements that had similar properties. So in most of these cases, and we'll learn this, if you go down a group, they have similar properties, these columns. And some of them have names that we'll learn before these slides are done. So not including hydrogen, starting with lithium and going down to francium, these have similar properties. What is the property? One of the properties, they react violently with water. So as you go down, they start actually responding more violent. So lithium responds violently with water, but sodium responds even more, stronger violently. I know that probably is not a correct way of saying that, with water and so forth. As you go down, it's a stronger reaction. So that is a property of behavior that these elements have in common. And then we can go through with some of the other ones. So what you first need to know is periods and groups. This is very similar to, remember I told you these atomic numbers are like the address. these are the streets. So if I needed to tell you to locate something in period 4, group 2, how would you do that? Well, you go to period 4, 1, 2, 3, 4. Group 2 is here, group 2A. But if we remember, I told you we're not focusing on these. So if I said 3, then you can go across 3 right here, period 4, group 3. If I said period 2, group 8, so period 2, group 8 is neon. So these are like streets, if that's what it makes it easier to understand. This is how we pinpoint something that we're looking for on the periodic table. Okay, so again, when discussing elements and the periodic table, we use abbreviations. They are made up of 1 or 2 letter abbreviations. These chemical symbols represent the element. Most come from English, but others come from Latin, Greek words, and as you start going down into some of these down here, they get named after, I think one was even somebody's dog, if I remember right. They're interesting. Some of them are interesting. I'm not going to go through them right now. Others are named for people. For instance, let me see if I can remember which one it is. I think it's 109. That might mean for Lise Meitner. She was a woman that played a big part in chemistry, but because she was Jewish and a woman during World War II, she was pretty much ignored and her credit was given to other people, unfortunately. So they gave her, I'm pretty sure that's her element on here. So carbon is C, hydrogen H, magnesium is, and you will definitely need to know these. I know we're at home, but trust me when I tell you there's certain things that if you learn how to memorize, and not just memorize, learn them, you will save yourself much time, because we're just build upon and build upon. So if you start this early before we start learning more stuff, you end up with a very strong knowledge of some of the stuff that you don't have to spend more time on the way other people will struggle. Basically what I'm saying is start out with a very strong foundation and it will pay off, even if you have to put more time into it. Okay, so again, we have 7 periods. We have 18 columns. And the older way is the 1A to 8A and then 3B to 12B. But your book is showing you the A's and then the 1, 2, 3, 4, 5, 12, 13 to 18. Both ways work. Both ways on here, you'll always be given a periodic table. And after a while, believe me, you'll start knowing where most of these elements actually are located on here. So now we're going to look at these colors. Why are they colored the way? And if you do Google, you'll find different colors. You'll find that it's very interesting. Other names, sodium is Na for the Latin name of natrium. Iron is ferrum, Fe. Copper is Cu, cuprum. And lead is plubum. So this makes sense. This shows you why, some of the names don't match the way we know it. For instance, silver is Ag. Gold is Au, mercury is Hg. So some of them can really throw you off from the way that we would think of them being. Okay, so blocks of elements. I pulled this from my files because I like the fact that it is colorful. It stands out. And this is from these slides. I don't like that they use these dull gray colors. One of the things here is metals. If you see this blue, everything, you see that most of the periodic table is a metal. What's green is a non-metal, and then we have these metalloids. Metalloids are a combination of properties of metals and non-metals. And I kind of like the colors because they really stand out, and the slides that were given to me, they don't really stand out. So blocks of element, light tan areas, which I totally don't light tan. Why would they just do contrasting colors? The blocks of the elements on the left and the right sides of the main periodic table are the main group elements. So what does that mean? When we discuss main group elements, we're discussing these here and these here. This small rectangle and down here, they are their own, and we will definitely cover them. But when we talk about main group elements, and if you're asked that, it's these and it's these over here. Elements in the middle are called transition elements or transition metals. And these are called inner transition elements or inner transition metals. So there are names: main group elements, transition metals, transition elements, and then inner transition elements or inner transition metals. Okay, so again, I pulled one of my colors because I think it just is prettier and it stands out, and I'm a visual learner, so I need things like this. All right, so we're going to now look at metals, nonmetals, and metalloids on a periodic table. By the way, I just Googled. You can easily Google any of this stuff. If you are needing help with it, you can do periodic table, metals, nonmetals, and you can find images, and you will find anything and everything you need on here. This is from another book of mine at another college. The elements in the periodic table can also be classified as metals. So not only can we classify things that are similar in properties going down, we can classify them as metals and nonmetals and metalloids. And here's you can see I forgot what you call that, menu? No, I can't remember what it's called. Anyways, the heavy zigzag line separates metals and nonmetals. Metals are located to the left, nonmetals are located to the right, and metalloids are located in the middle on the staircase or heavy zigzag. Okay, so properties of metals. Metals have they're different properties compared to nonmetals. Metals are shiny. Now this is just general terms. Some metals are different than others. But most of them are shiny. Think of gold, think of silver. Ductile. Ductile means drawn into wires. Remember, we use electricity in our homes. We're using wires. Those are metals. Malleable, flattened into sheets. We can hammer them into flattened sheets. They conduct heat and electricity. They are solids at room temperature. The only one so metals are solids at room temperature. Even salt, sodium is a metal. Even it may not look so that it's sodium, which I probably should have a picture of it in here and further slides. It is a shiny, looks like a metal. It's a shiny metal. But we think of sodium chloride as a salt, and that's where a chemical reaction has occurred. So what sodium actually looks like compared to sodium chloride is entirely different. They are solids at room temperature. The only exception is mercury. Mercury is a liquid. If you have an ultramometer, then you will see that it has liquid mercury, which is like a silvery liquid. That's mercury. Metals tend to lose electrons when they undergo a chemical reaction. So for instance, sodium chloride, everybody knows what salt is. Sodium will lose its electrons and join with chloride. And chlorine will take the electrons. And that allows this bond between them that makes sodium chloride. But chlorine on its own is a very deadly gas. So it's very different from the properties that we know of sodium. Metals tend to lose electrons. So when I say that, that means this nice blue, they tend to give away their electrons, some of them easier than others. Iron, nickel, and platinum, those are examples of metals. All right. Metals lie to the left of the periodic table. So here's some examples. Here's some gold, here's some silver, we have copper, and we have iron. These are the transition metals in this bottom part right here. This starts from column 3 to column 12. These are the inner transition metals or inner transition elements that are here. And the first column is lanthanide series, and the second one is actinide series. So the transition elements are 3 to 12, and they're called transition metals. So if I say transition metals, it's from 3 to 12. They tend to be harder and less reactive than the metals of 1 and 2. 1 and 2 are very reactive metals, meaning when I say reactive, that means they are practically throwing their electrons at another element. They don't want them. They want to get rid of them as fast as possible, like it's a hot potato. If you guys ever played that hot potato game. The columns, the transition metals from 3 to 12, they don't give them up as easy. Some of them give them up easier than others, but they definitely, none of them give them up as easy as columns 1 and 2, which consists of, if we go down, like lithium, sodium, magnesium, calcium, barium. The inner transition elements are metals also. All of this is metals. The first row is lanthanide. These contain heavier, naturally occurring metals called rare earth metals. You really can't see it right now. The second row is actinide. Some of these, like I said, basically have existed only for seconds, but long enough to say they existed. So here, so this is uranium, and then after that, all of these are man-made. So though a few can be found in nature, is what it said. Um, but yeah, these are very different from what we normally deal with up here. These are the ones that we're going to focus on. Okay, properties of nonmetals. Unlike metals, which tend to have the same properties, which I've shown here, um, properties of nonmetals, they're different. They are all over the place. One element might be next to another element and be vastly different. So they are, but the general of it, they tend to be brittle, they're dull, and they're poor conductors of, but often good insulators. Poor conductors of electricity. They have low densities. So remember we were discussing densities, things that float on water, things that don't, and have very low melting points. How low? Well, most of these are gases at the top, and their melting points are like let's say an example, negative 100 and something, which we're not at. So in order for it to be a solid, we have to get down to negative 136 degrees. We're not at. That's why we know it as a gas and not as a solid. Nonmetals have varied properties. Some are solids at room temperature while others are gases. Nonmetals tend to gain electrons. So all these blue, they give the electrons to the yellow. They are practically throwing them at them. I'm being dramatic, but they give them to the yellow. And the yellows want to take them. They want to take them as fast as they can. So nonmetals tend to gain electrons when they undergo chemical changes. Good examples of nonmetals are oxygen, nitrogen, chlorine, and iodine down here. They will take the electrons away from anything that's blue. Hydrogen is here because it has one proton. However, it's yellow, it's over here, so do not get it confused with the rest of this row column here. That's family, that own family. Properties of metalloids. Metalloids are connected in that staircase. They exhibit properties of metals and nonmetals. So they have a combination of both. They are better conductors than nonmetals, but they're not as good as metals. Metalloids are semiconductors because of their intermediate electrical conductivity. One of them is silicon, which is what we use in calculators. If you have I don't even know if anybody have calculators that aren't, with a little solar window in them anymore. These properties make semiconductors useful in the manufacture of, that word doesn't look right now, of electronic devices that are central to computers, cell phones, and other modern gadgets. So silicon, arsenic, germanium are good examples of metalloids. They have different properties of metals and nonmetals. So here's a chart so you can compare the differences. We have silver, antimony, and see, this is a good one. Does not match what the actual name is because it's in another language. I'm guessing it's probably Latin. And then sulfur. So sulfur is very dull and brittle. If you touch this, it becomes a powder. Sulfur smells like rotten egg. Here's antimony, and then here's silver. So metal, shiny, extremely ductile. Remember, these can be made into wires. Malleable. Malleable means sheets, hammered into sheets. Good conductor of heat, electricity. Used in coins, jewelry, and tableware. Has a density of 10.5. They tend to be very dense. Melting point is 962 degrees Celsius because it is a solid. It would have to get to this in order to start changing. Antimony is a blue-gray, shiny, brittle. That matches the nonmetals. Shatters when hammered, so it's not malleable. Poor conductor of heat and electricity. Used to harden lead, color, glass, and plastics. Its density is not as much as this, but far more than this one. Its melting point is 630 degrees Celsius. Now if we look at sulfur. Sulfur's yellow. It's very dull. It's a powder. It's brittle. It shatters when it's just a powder. If you break this, it goes into a powder. It's poor conductor of heat and electricity, but it's a good insulator. Used in gunpowder, rubber, fungicides. Its density is very low compared to the other ones, and its melting point is also very low compared to the other ones. All right, so let's do some, again, I didn't have access to the homework, but I pulled some of my old slides. Identify each of the following elements as a metal, nonmetal, or metalloid. So sodium, let's look for sodium. It's here. It's blue, and it's on the left side of the periodic table. So I'm going to just jump ahead, and it is metal. What about chlorine? Well, I already discussed chlorine. It's yellow. Now keep in mind, yours, this printout that you did, it's not going to show like this. So if you want, I would get a pen and mark where everything is, like an outline, so you know where the metals are, or even just the outline of the metalloids, so you know which side is which. All right, so chlorine is yellow, so it's a nonmetal. Where is it at? It's atomic number 17. Silicon is a metalloid. It is number 14. Iron, I've already pointed out, is 26. It's a metal. And carbon is a nonmetal. It is here. It is number 6. All right. So one more thing we have to learn. Remember I told you that going down a group is some of them are named their families. Well, this is alkaline earth metals, group 1. Alkaline alkali metals is 1. Alkaline earth metals is 2. Some people are creating names for these, and yes, if you look online, you can find names for them, but they haven't really stuck. So your book doesn't want them, so I'm not even going to bring the names up. 17 is halogens, and 18 are noble gases. These are names you definitely need to know, and you need to know what column. 17 or 7A. All of these, just subtract 10 if you have a hard time. That's all these are. 18 or 8A, 1, 2, these never change really. 13 or 3A, 14, 4A, and so forth. Use the letter B for transition elements. So this, I think I got this from another book, and they put a B here, but your book doesn't. So it just goes from 3 to 12. These are transition elements. All right, so let's look at alkaline metal. Alkaline metals are the furthest right, and they're in group 1. Hydrogen does not count, so it starts at atomic number 3, which is lithium. And remember I told you the sodium looks like a shiny metal? It can cut into, this is very dangerous to work with, extremely dangerous to work with, and I've worked with it. I have to take all this protocol in order because it looks like this if something goes wrong, and it reacts with water. So by adding water to it makes it worse. So I had to be very careful with it that anything I used didn't have water in it at all. I can slice this like butter. It's just very interesting but very dangerous. It's a soft metal and it reacts violently, and I used to have a picture and I couldn't find it of all these metals reacting with water, and you can just see it's getting like more explosive pretty much. So that is alkali. So if I ask you about alkali metals, it is group 1. If you have a printout, this might be a good time to make a note of what this is. Remember that printout I told you guys to have? Group 2 is alkaline earth metals. This is beryllium, and it goes down to, of course I put myself in a spot. Sorry, this is radium. My brain went out on me for a little bit. This is radium. That's here. This is less reactive than group 1, but it burns brightly. So strontium, which is this one right here, is responsible for the deep red color in fireworks. Magnesium gives off a very bright white color. So we're going to start doing a flame test and cover that in chapter 4. You're also going to do a lab, which I would tell you when you're in person, this is actually one of the coolest labs because you dip these in solution and then you light them and you get to see the colors right in front of you that these metals give off, and they're really pretty. So this is where fireworks come from on some of these. So they are right of the alkali metals, and one of them is strontium that gives off, there's others that give off red, but they give off a different type of red. And this one gives off a deep red, and magnesium gives off a bright white. So light white, so bright of a white that you're actually not supposed to look directly at it. This is interesting. I always thought this is funny that when you do a lab with it, you hold this metal magnesium ribbon, and the lab says, every lab I've done this at every school, it says don't look at it directly. But to me, it's like, well, also how are you supposed to know that the small tiny ribbon is making it into the fire, into your Bunsen burner? But you manage to do it without looking directly at it, and it's so bright that you still see it out of the corner of your eye. So group 2 is alkaline earth metals, and it goes down the column. This is a family, and they have similar properties. They're just less they burn brightly, and they're less reactive than group 1. Okay, halogens. So we jump over here. These are halogens. Everything that's here, and I got this from a different book. So fluorine, chlorine, bromine, and iodine. They are diatomic molecules in elemental form. What does that mean? That means that in nature, they're found like this. This is why I added this slide. They are found in 2. Di means 2. So 2 atoms are considered a molecule. So this is found as all of these. This is a gas. This starts going into a liquid, and you see here is a solid at the bottom. They still have vapors attached to them, but as you go down, they get bigger, and it starts getting into a solid. This is a liquid. This is just a gas. So, and you can see this one's more clear. This is a very dangerous gas that was used, I believe it's in World War I. That is very dangerous. In the 70s, I am a 70s child, and when we cut ourselves, we used iodine that burned like nothing else. Everybody had iodine in their house, and you can still buy some and use it on cuts. It burns. Now we use hydrogen peroxide, but not back then. Oh, I don't know what hurt worse, if you cut yourself or putting that stuff on. So anyways, these are diatomic molecules. That's why I included this, so you can see this is how they are found in elemental form. They are naturally found as 2. There are 7 diatomic molecules on here. We have oxygen is another one that's found as O2. Hydrogen's another one, but right now we're talking about halogens, which are 7A that go down, or 17, depending on how you look at it. So halogens, we'll use a lot of these here. Halogens react really quickly with metals. They will take those electrons away from a metal, and other nonmetals, in fact. They will take pretty much electrons from anything near it. And halogens help make substances such as bleach, Teflon, fire retardants, and table salt, which is what everybody should be familiar with, is sodium chloride. Okay, and the last one we're going to look at is noble gases. Noble gases are generally, they do not form compounds. They are so the main thing about chemistry, and it doesn't change, is it's all about lowest energy. What is in its lowest energy is also the most stable. And everything always tries to go to the most stable. So when the fact that noble gases do not generally form compounds, it means that they are very stable by themselves. They do not want to react with anything because they don't need to. And that's what it means by they don't form compounds. They don't attach them. There's not, I talk about H2O, which is water. Other things react with other things because they're not stable until they join with something else. However, these are so stable by themselves, they just leave me alone kind of attitude. They are all gases at room temperature, and they give off, like for instance, neon gives off this color here. Helium is a gas. So we can see that they're all gases, but some will give off colors, and we know others for other things, like as balloons. If you have double pane windows, you most likely have argon gas in between the 2 double panes. There should be some sticker that tells you that. These are also very inert, which means they don't react because they don't form compounds. They don't want to be bothered. That means that they also are very stable, and that's why argon would be used as an insulator between these 2 double pane windows.